Good morning, neighbors. Monday morning, quiet, rainy, soggy outside, a little too soggy. We've gotten a lot of rain, but still not enough across the state. Parts of the state have done well. So, hey, bit of coffee. So, this is a concept, applied physics, interesting thing that has an evolutionary tale to it on how it changed and got different, and yet it's going to be hard to understand. The way I understand it is I saw it applied, I guess, on instruments, on math, on a chalkboard, on discussions for days and weeks in a class, because it has to do with signal processing. A pretty huge field of information technology called DSP, Discrete Signal Processing. In order for a signal to be discrete, you have to identify that it's discrete, right? What does that mean? And it just means unique. Very soft concepts we're talking about here until you go apply it to something. So in this case, fast Fourier, F-A-S-T-F-O-U-R-I-E-R transforms is a good Google. And the explanation of it is provided, of course, by Wikipedia, because Wikipedia can be a very good lead-in to questions, to thoughts, to ideas. But this fast Fourier transform, this basically, how I saw it, is you've seen an oscilloscope, and you've seen the sine wave on an oscilloscope, and now you've invented something to look at that sine wave. And it's not just your eyes will tell you something. The screen will be able to give you some statistics back about that sine wave. The frequency of it, 60 hertz. The voltage of it. The amplitude of the sine wave, peak to peak amplitude, 120 volts. That would be AC wall plug you're looking at. So if you recognize the signal, you know how to read the gratings, the graticules on the CRT, then you would recognize you're looking at a sine wave. But now I hope you jumped ahead to the fast Fourier transform page on Wikipedia. It's just concepts. But this is how ideas are turned into machines. Let's call it artificial intelligence. Very restricted, very bounded. So looking at this fast Fourier transform, this is a piece of software now. It used to be done in hardware. It used to be done with deadbeat oscillators. Not related to deadbeat dads, but deadbeat oscillators are still used. They've just changed. They've gone electronic. So this fast Fourier transform is a piece of interrogative software. It's also a piece of predictive software because what it assesses from a very small piece of information on a waveform, what and how it assesses that can make predictions about the waveform. If you look at it twice and it's starting to decrease, then you should correct the voltage to keep it up to 120 volts. That's what you want, is a 120 volt line. It's not always 120. It's rarely 120, as a matter of fact. So this fast Fourier transform, I mentioned DSP, discrete signal processing. Finding the signal in the first place has evolved, gotten better. We used to do it in very old, what I would call mechanical ways, electronic mechanical ways. And now we do it in computer ways, which places equations inside the computer that do analysis that we can do, only it can do better. And once we learn what it does, we learn how much better it can do it. So this fast Fourier transform, if you're looking at the pictures from Wikipedia, Their picture is showing three waveforms overlaid. You could have thousands of waveforms overlaid and have to try to pick a signal. Each one of those waveforms, these are all the same frequency on this picture that they're using. So, very interesting tool. Where did it come from? Where did it get refined? Mathematically, in calculus. Mathematicians, physicists, were able to derive from what they'd seen with these simple waveforms to pick meaning out of much more complicated waveforms. So it's fascinating, that the evolution of the technology that has us here today, the pieces, the tiny pieces of what appear to be artificial intelligence that are nowhere near that. So this fast Fourier transform could be used to interpret whatever type of wave you can think about, whatever waveform you can think about, with the proper electronics receiving the signal properly to get it into the computer to be able to, so it just got very complicated. Discrete signal processing. This is radar systems. This is radio. This is AM, FM. All of the spectrums, the frequencies involved in the multiple ways. I mentioned AM and FM. There's single sideband, upper sideband. There's many different modes of radio frequency communications. Now we have optical frequency communications, which is typically fiber optics. Now, we used to do this with smoke signals. That was probably one of our first optical transmission lines, was smoke signals. Then we developed mirrors, flashed mirrors at each other, maybe. So we do this optically. We can use these same techniques optically because, oddly enough, colors are a frequency. These equations, this fast Fourier transform, this physics calculus-derived equation that has been proved, and when applied properly, quotes, it works, is an amazing piece of technology. There's little engineering houses all over the place that use this to do things and figure things out. It has very much to do with those radio antenna towers around you, those Wi-Fi towers. What's the scary thing? The new 5G. Energy at a distance can be harmful, period. It's not a question. It's a matter of how much, period. And light, closer you get to it, the harder the burn. Atomic emissions, the closer you get to it, same deal. Radio frequency waves, same deal. So, this fast Fourier transform, you can find some new electronics. A little computer card plugs into your computer that can receive these airwave signals and display them to you. This is called SIGINT, signal intelligence. And that goes in both directions. You signal intelligence to know who and what you're talking to, right? So, this fast Fourier transform, a mathematical equation derived from man's visual observations about the world and the effects of frequency over time. Frequency over time is calculus's key tool. It adds that third dimension to a chart or a plot or a physical entity, because what it is today might have rusted away to something else tomorrow. Fast Fourier transforms. I know, this is a what the heck, but imagine being in an engineering world where this was you walked in the door in the morning And this was your life, staring at these transforms and information, because to get to the ability to do these transforms, I have to find the signals I'm looking for, have an idea they're even there. People dedicate their lives to this type of thing, this fast Fourier transform. We point them at satellites, friend and foe, in order to find out information or even receive the signal and process it. The days of tuning the dial and a capacitor back there, changing the frequency of your tuner, have changed. Some of those don't work. The frequencies they used to work on have been reallocated to something else, so you might get noise. Ham radio folks know the concepts of these well. You can turn the tool on. It's a cheap board with a good piece of software, and start to use it without knowing all of this behind the scenes things. But this fast Fourier transform is one of probably the most dramatic game changers in signal processing, created generations ago, evolved to be with us and match our whatever is working up here. So, fascinating topic, especially when you see it applied through your career. When you take those tips and you begin to look at data sets using these fast Fourier analysis tools, looking for trends inside of who's buying what. What's the trend lines? If I sold this much this year, could I sell this much next year? You can apply these types of formulas to the seasons and the buying habits and the oil consumption and the casino tables. Because humans are amazing animals, aren't we?